Welcome to this fourth tutorial in the mini-series on calculus at the higher level. Now, in the previous tutorial, we, from first principles, derived the derivative of the function f of x equals x squared, and we found it to be 2x. We also very quickly derived the derivative of the function f of x equals mx plus c, a straight line, which we found to be a constant, and that constant being the slope of that straight line. No surprises whatsoever in that case, given that we know the derivative of a function is the slope of the tangent to that function. Now, in this tutorial, we're going to take a big leap and we're going to derive from first principles the derivative of a function f of x equals x to the n, where n is a positive integer. This is often a formula that is thrown at students without really any derivation, and you will find yourself using it a lot actually in calculus, but it's much better to derive it first of all, then you can be sure for yourself that it's true, and it will have no mystery for you. It'll be a very straightforward thing. Now, as a wee warm-up to this, what we're going to do is actually quickly, following sort of the pattern we did in the previous tutorial, we're going to derive the derivative for a function f of x equals x cubed, the simplest cubic function. And that will just, I think, give us enough insight into how we do the general case of x to the n. Right, so let's just warm up then with f of x equals x cubed. Do a quick sketch. And if you haven't seen a graph of x cubed before, it's sort of visually, for positive x, looks a bit similar to a parabola. For x equals 0, this function is 0, and then it rapidly increases with x, like that. The difference to a parabola, though, is that we're cubing x, and the cube of a negative number is a negative number. For example, negative 1 cubed is negative 1 times negative 1, which is positive 1, times negative 1, which is then negative 1. So for negative x, y will be negative, and this function will look like this on the negative side. And that is a rough sort of sketch of the function x cubed. Right, now we're just going to do this sort of, I think I called it a Gedanken graph, which is probably a terrible word. Terrible collision of English and German, for which I apologize. But let's just get a sense here of what we would expect for the derivative. Okay, so f primed is a function of x. There we are. And let's just remind ourselves that f primed is going to be the difference in the function, the difference in the output, divided by the difference of the input, and taking that input, difference in input, to 0. Okay. Let me just write this out a bit more formally here, just because we will be using this expression in this tutorial a fair amount. Okay, so we've used this now a couple of times and we're becoming more familiar with it. So again, we're going to have near the origin here, as we vary x, there's almost no deviation in the output, so we know that this derivative must be very, very small, if not 0, around the origin. It's going to be something which increases as x increases, because we saw that happen with the parabola, that for a given difference in x here, let's just show that again. There's quite a good concept here, so we might as well repeat it. So for a given difference in x here, the difference in the output is very small, but out here, that given difference in x actually has quite a large change in the output. So the derivative, which is the translator from a change in x to a change in y, as it were, goes from being very, very small to much larger. So we're sort of expecting, something like this. And then on the other side, by symmetry, because these two curves are the same except for the sign, we would just expect the same thing in terms of the magnitudes. Here, because the derivative is the right output, take away the left output, here we're taking this value, take away this value, we will actually get a positive outcome for that. Okay, so these clouds are going to be positive on the left hand side. Remember, they were negative when we did the case of the parabola, but here they are both positive. And you can sort of, imagine what that curve might be. Okay, I'm not going to say what it is, but you can sort of imagine what that might be. And let's just derive it using this fundamental formula here, which defines the derivative. So for this particular function then, and remembering, at the risk of being super boring, that we have f of apple, which will be familiar to you if you've watched the functions videos, f of apple, where apple is x plus delta x, and f of apple is apple cubed. So this f primed then is going to be x plus delta x all cubed, take away f of x, which is just x cubed, divided by delta x. And at the end, we want to take delta x as arbitrarily small, essentially to 0. Now, I'm not going to expand this out slowly because I don't really have space, and I'll let you do that at your own leisure. But if you've had a bit of experience multiplying out brackets, you'll easily be able to derive what this is. You can just think of it as x plus delta x times the square of x plus delta x. We found out what the square of that was in the last tutorial, and we're just going to multiply that again by x plus delta x. And what you'll get is x cubed. You'll then have 3 lots of x squared multiplied by delta x. You'll have 3 lots of x times delta x squared, and you'll have 1 lot of delta x all cubed, and then finally we have take away x cubed. Looks like a bit of a mess. Don't worry, we're not going to use this kind of mess anymore with these kinds of derivations. I'm just doing it very completely here because it's an introduction, and then we divide by delta x. So let's just have a look at this then, and as I say, you'll be able to check this very easily for yourselves by just multiplying out this product of 3 brackets. Well, this x cubed here cancels with that x cubed, and we can divide by delta x because all of the terms remaining have a delta x. So we can have, there's a common factor of delta x on the top and the bottom, so we can divide by delta x and we get 3x squared. We get 3x times delta x from that term, and finally this last term gives us delta x squared. And then at the end of this, we want to take delta x to 0. So these two terms will vanish when we take delta x to 0, and we are left with the answer, which is 3x squared. So that is the form of the derivative of the function f is x cubed. We get 3x squared. And that passes our plausibility test because by looking at the change in the function for a given input, we could see that we had something, we wouldn't be able to say it was a parabola from this, of course, but it's something that looks like it could be a parabola, and indeed it is a parabola. There's no way that we could have found this coefficient 3 here. But yes, indeed, this, it turns out, is a parabola. Fantastic. So that's another notch on our belts in deriving derivatives. Now, the one part of this derivation that may have been rather unsettling was all of this detail here, multiplying out all of these terms, and we're not going to do that again because you don't have to do that. I think what you can see is that you only really need the term that has a delta x multiplying it, because ultimately we're dividing by delta x and taking delta x to 0. So all these higher terms, which are tiny and get increasingly tiny as we take delta x to 0, are irrelevant. And this is the beauty of calculus. It's a great simplifier. All of this stuff is irrelevant. So ultimately what we're doing is picking out the term proportional to delta x. We can think of it as the leading term in the expression for small delta x, because with that leading term, dividing by delta x leaves us with something which is independent of delta x, and then when we take delta x to 0, everything else vanishes, and that thing that's left there is indeed our derivative. So I'm going to use that sort of more experienced and direct way of thinking now to do the general case. So let's just, like we did before, sort of mark out a bit of territory for ourselves here, because we'll need as much space as we can get. I'm not going to plot any functions now. I'm just going to do some brute force algebra to get this derivative. So we're going to look at the general case. F of x equals x to the n, where n is an integer, and it's going to be an integer which is greater than or equal to, let's just say 1 for our purposes, okay? And for the sake of this derivation I'm about to do, we don't have to specify a value of n. It's just arbitrary. But maybe intuitively, when you see the way I'm going to do the derivation, you might think of n as some largish integer, because it will actually make a bit more sense just with the way I'm going to write out all of this here. So this is the formula that we're going to use to get the derivative. The only hard thing in this formula is f of x plus delta x. And what we've seen is that the intuition we're gaining, the experience we're gaining, is what we need to get from this is the very leading term, which is actually just f of x, plus the next term. So we just want the leading term, which is going to be x to the n, but then we want that next term, which is going to be proportional to delta x. And then everything else is going to be higher powers of delta x, all of which will be blasted to 0 by this limit that we take of delta x going to 0. So let's have a look at that then. We're interested in f of x plus delta x. F of apple is apple to the n. Our apple here is x plus delta x. So this is equal to x plus delta x to the power of n, where n is some unspecified positive integer. Okay, that's good. Now you might think, well, hang on, if we don't know what n is precisely, how on earth can we make any progress? And I just want to show you that absolutely we can. And this is kind of a nice demonstration. As you get more experienced in maths, it sort of becomes, I don't know, it's sort of like being in a workshop, making stuff with tools that you find certain, ways of doing things which are the ways of the crafts person, which are sort of straightforward ways to get to your endpoint without having to sort of go, through lots and lots of actually quite unnecessary details. So a change of colour is in order, and let's have a look. What does this actually mean? Well, something to the power of n means that we're multiplying that thing by itself n times. So this literally means x plus delta x times x plus delta x times x plus delta x, and then times them, and then x plus delta x, x plus delta x, with in all there being n of these brackets. So that's what this literally means. It is a string of brackets all multiplied together, and there are n of them in total. Now let's remember that delta x is very small, so we have big plus small times big plus small times big plus small, and then plus times big plus small times big plus small n times. Now just let me make a point here. There will be people watching this who are natural skeptics, and that is excellent, because it's good to have a skeptical mind when you're learning maths, because you don't want to be sold a lemon. You might say, well, hang on, why is that big plus small? I know delta x is small, but what if x was small? And that's a good question. And the answer to that is that when we talk about taking delta x to 0, we really mean that we are allowed to take it arbitrarily small. So no matter how small you take x, we are always at liberty to take delta x much smaller than that value of x. So this is always going to be big plus small times big plus small, and so on and so on and so on. Now here comes the magic. The biggest term is going to be when we select from each bracket the big thing. So we have big times big times big, and then dot 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 times big times big. And that will be by far the biggest thing that comes from multiplying all these together. And it is the big thing, which is x, multiplied by itself n times. Which is no surprise, because we've seen in the past that when we look at this f of x plus delta x, the thing that sort of comes out front is just the original function, and that is our original function. So let's ask ourselves, what's the next biggest thing that we can get from this string of brackets? Well, the next biggest thing will be some term where from n minus 1 of the brackets we take the big thing, and then from one of the brackets we take the small thing, namely delta x. So the next term has to be something like, and I'm just going to sketch it before we really think it through, something like n minus 1 lots of the big thing. So from n minus 1 of these brackets I take the big thing, which is x, and then from just one of the brackets I take the small thing, which is delta x. And there's going to be some constant there, and actually our job is to work out, well, what's that constant? And this is something that you may have seen before if you've done probability theory or permutations, because what we're really doing here is sort of like a permutation type problem. We're saying, well, how many ways could I have selected a small thing from the n brackets? Well, I could have taken the x, the big thing times the big thing times the big thing, dot 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 times the big thing every time, and then on the very last go take the small thing, and that would be one way to get this term. Alternatively, I could have taken all big things until I got to the penultimate bracket, and then taken the small thing, and then taken the big thing in the final bracket, and that would still give me this term, but it would be a second way of doing it. And so instead of doing the last or the last but one, I could have done the third from last or the fourth from last, and you see that there are actually n different ways that I can select the small thing and then take the big thing from all the other brackets. So the coefficient here actually is very simple, it's just n. There are n ways to select one small thing and n minus 1 big things. Okay? Now we're not going to derive in detail the next term, we don't need to. We should just make sure though that we understand how big it is, roughly. Well, the next term is going to be where we take the big thing from n minus 2 of the brackets, and the remaining 2 brackets we take the small thing. And there will be some permutation of how many ways that we can do that, and we're not going to worry about that. So I'm just going to say there is some little green cloud, a number that multiplies this, that we're not even going to bother calculating, because you know what, we don't need to. And there will be other terms that we're also not interested in. There'll be terms with delta x cubed and terms with delta x to the fourth. And the very last term in the series will be just taking the small thing from every bracket, delta x to the power of n. But you know, all of that is fluff. We don't need it because, as I've argued previously, we just care about the very leading term, which is just the original function, plus, and this is where all the action is, the next leading term here that is proportional to delta x. So here we go. F primed then is this thing that we found. Take away the original function, all divided by delta x. So I have x to the n plus n x to the n minus 1 delta x plus all this other stuff, okay, which I'm just going to draw as a big green cloud. I'm pausing because there's a very formal way of writing this, but I don't want to throw extra notation at you. So I'm just going to say delta x squared dot 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 in quotation marks, because you know what I mean. It's all this stuff, okay? And then take away f of x, x to the n. And then that's all divided by delta x, okay? And ultimately we're going to take delta x to 0. So great stuff. This is very familiar to us from looking at the parabola and the cubic. Very, very similar. This very leading term cancels with the original function, and all the magic occurs here. We divide by delta x, so there's a common factor of delta x that we can divide through by, and what we're left with then is n x to the n minus 1 plus the green cloud times delta x dot dot dot, which I'm putting in quotation marks because I don't want to throw extra notation or boring details at you which are irrelevant, because we're taking delta x to 0 ultimately, okay? And when we take delta x to 0, all this stuff, hasta la vita, gone. And we have our final result, that the derivative of x to the n is this beautiful thing, is nx to the n minus 1. Voila. So congratulations if you've managed to follow this derivation here. We can easily make it a bit more formal, but actually this is indeed actually fairly rigorous, and all of the concepts are here. So if you followed this through, well done, because you have now differentiated x to the n. Fantastic. And we have this beautiful result, that it's n times x to the n minus 1. And let's just check that with the ones that we've derived a bit more, in a bit more of a kind of laborious way. Well, if n equals 3, it would be 3 times x to the 2, which agrees with our cubic derivation. If n equals 2, it's 2 times x to the 1, namely 2x, which agrees with our derivation from the previous tutorial for the parabola. If n equals 1, so we just have f of x equals x, we have 1 times x to the 0, which is just 1, which is correct if we just have a straight line, as we saw before. And in fact, even though I said n greater than or equal to 1, because I didn't want to kind of be too sloppy here, drawing all these brackets down, if n were actually 0. But if we do take n equal to 0, we see that f primed is 0 times x to the negative 1. And so long as x is not equal to 0, that would actually give 0. So this formula almost kind of gives you the answer if you have n equals 0. You don't need all of this to know the derivative of f of x equals x to the 0, because x to the 0 is just 1. You just have a constant, and its derivative is 0, because the change in the output is always 0 regardless of any change in the input. So let's just say that there. So it all checks out with what we know, common sense and derivations we've done. This all checks out, and this indeed is the correct outcome for the derivative of, the derivative of this function f of x equals x to the n. Okay. I'm going to put an exclamation mark there, because I think we should all feel quite proud of ourselves, because that is a beautiful piece of maths actually, to derive that derivative, and very satisfying. Let me just say a couple of words now. I think it's very good to have seen these derivations. I think it's very good to be able to reproduce them if possible, but it gives you a very, very intuitive understanding of calculus, because really the guts of calculus is this term here. It's pulling out this next to leading term, is what we mean actually by the derivative. And these higher terms actually also have very interesting meaning that you'll come across at advanced higher in terms of what are called higher derivatives. So there's a lot here actually. So having your hands on calculus in this level of detail at the beginning is very, very healthy in my view. What I'd like to turn to in the next tutorials on calculus is deriving the derivatives of the trigonometric functions, sine, cosine and tangent, and that's going to be really interesting for us actually, and the results are quite beautiful. In order to do that, I will need a bit more knowledge of trigonometric functions than we've seen at the National 5 level. So I'm going to give some lectures now on trigonometry. So I'm going to pause the calculus lectures. I'm going to give some lectures on trigonometry, and that will arm us with a bit more trigonometry so that we can do the same justice to trigonometric functions as we've done here, and actually with our hands derive the derivatives. And you'll see that's a very satisfying exercise and very beautiful. As a very last point to make, you might ask, well, hang on, what if n wasn't an integer? What if we just had x to some powers? Say it was x to the half or x to the 9 quarters. What then? Well, I'm not going to tell you what the answer is for that. Often you're given that answer right at the start of calculus, which is really a shame, because that's actually quite a deep question. There is a very, very nice way to derive the derivatives of arbitrary powers of x. But for that, we need to know something about functions called exponential functions and logarithmic functions, which have a lovely, wonderful existence within calculus. So what I'm going to do is do trigonometry, look at those derivatives, and then we're going to cover exponentials and logarithms, and then we're going to look at those derivatives, and that's going to answer that question about x to a power which might be non-integer, say a real number. Right, with that I will pause here. I hope you found that enjoyable and possibly even fun, and I look forward to seeing you next time.